Hi everyone, my name is Sobin Bonk. This work has been done in Disney Research Lab in Pittsburgh and is about person re-identification. As you might know, person re-identification is a problem where you want to determine whether a particular person of interest has appeared over a network of cameras. And as of course clothing features are not as distinctive as face or iris, we cannot expect the high accuracy in the performance, and it's why we treat it usually as a retrieval problem. In this case, we would like to have a framework which returns us the list of the most similar signatures, where the desired or searched person is as close to the first rank as possible. We represent image by the set of features. First, we divide image into the rectangular regions from which we extract the color histograms in different color spaces, sift or other texture features. Then for such image region, let's call it patch, we follow this framework and we create a high dimensional feature vector, which usually in standard approaches is more than 20,000 features. So we would like to have images coming from this and images which contain different persons far apart. Right? We also will know forming metric learning approach, which is called Mahalanobis metric, where on the one side we have a positive samples and negative samples when we have images. There are two issues related to metric learning. We should significantly reduce the dimension. 20,000 feature dimensions. And second problem, that if we extract the features on the fixed grid, right, then the features might not correspond to each other, even though it's the same person. In this work, we propose two contributions. First is to, instead of learning the metric for the whole image, we propose to learn metrics locally for patches. By doing that, we avoid the strong dimensionality reduction. Second, instead of having a fixed grid, now as we learn the metrics locally, we allow the metric patches to change their locations. In this case, we applied well-known deformable part models, where actually the replacement of a patch can be controlled by spring constraints. We showed that our contributions bring significant boost in the performance in well-known reidentification datasets. Additionally, actually we performed the detailed analysis of what we learn, and we found that the patches which have which are on the similar locations might share the same metric. In practice, it means that we can learn effectively metric for matching people much faster with respect to the standard approach. For example, here this graph shows that standard approach will give us reasonable results after, let's say, 250 pairs of positive images, while our approach can give us the same performance given half of the training data. Thank you for your attention.